Hey everybody, let's do the 2004 mechanics free response problem number 2. And so let's read the problem. It says a solid disk of unknown mass and known radius r is used as a pulley in a lab experiment as shown above. A small a small block of mass m is attached to a string, the other end of which is attached to a pulley and wrapped around it several times. The block of mass m is released from rest, and takes a time t to fall a distance d to the floor. Okay, as shown here. So it looks like we don't know the mass of this disk, but we do know r, we know m, we know d. What else do we know? We know t, a time taken. And so it says, calculate the linear acceleration, A, of the falling block in terms of the given quantities. So what are the given quantities? I'm just going to list them here. What's given? So we know R, we know M, and little m is the mass of that. We know D, we know T, and we also know the initial velocity is 0, right, of this system. Now, you might be tempted to try and do this problem by looking at force. You might say, well, here's M, and here's, mg, and here's the tension upwards caused by the, the rotational inertia of this. But we don't know the mass of this disk, so we don't know the rotational inertia of this disk. So there's really no way I see to do that, but sometimes they give you more information than you need on these problems. Now, let's see if we can solve for A kinematically. I know for this block, I know the initial velocity is 0. We'll put it right here, v naught equals 0. I know the distance it's going to fall, and I know time. I know 3 things. If I know 3 kinematic things, and we have a situation where there's constant acceleration, I could just use the kinematic equations to do it. So now, my kinematic equations, I use, I know delta y, and I go, okay, delta y, t, and initial velocity, and I'm trying to find acceleration. Notice that I'm not trying to find the final velocity, and I don't know the final velocity. So which kinematic equation doesn't have final velocity in it? Well, it's this one. Delta y equals v naught t plus 1/2 at squared. Well, instead of delta y, we've got d equals, and then this is 0, and this is 1/2 a, forgot the t squared there, 1/2 at squared, and so 1/2 a t squared, and now we can just solve for the acceleration. The acceleration is equal to twice 2d over t squared, and that should give, that is the acceleration of this little mass in terms of the given quantities. We were given d, we were given t. Now we were given other stuff too, and we didn't need it to solve the problem. So be aware of that on the AP test. Sometimes they're going to give you more information than you need. Moving on to part B. The time t is measured for various heights d, and the data are recorded in the following table. So here's my data table, here's time. It says what quantities should be graphed in order to best determine the acceleration of the block. Explain your reasoning. Okay, so, look what I have here. I've got d equals 1/2 a t squared. Okay, that's the expression. If this is going to fall with a constant acceleration, these data should follow this mathematical pattern right here. So what should I graph? Well, in order to figure out what this is, I don't want to graph d as a function of t, because then I'm going to get a parabola, and I don't know how to figure out the acceleration of a parabola. But I do know how to find the slope of a straight line. And so I'm going to do this. I'm going to say let d equal 1/2 a, and I'm going to put this in parentheses t squared. Now why do I put that in parentheses? Because here's what I'm going to say. what's the equation for a straight line? I'm sorry. It's y equals mx plus b. Well, let's let y equal d. The slope's going to be 1/2 a. And what is our horizontal axis going to be? It's going to be t squared. So I'm going to graph d as a function of t squared. And that should make a straight line. Should make a straight line, then determine slope. So on the AP test, you can use abbreviated language and just try to, but this is how I would try to explain it to them. And how I would figure out the acceleration using those data. Okay. And so anyway, that's the way I would do this. So here's what I'm going to do. I mean, if I look at the next page, it says on the grid below, plot the quantities determined in B, label the axes, and draw the best fit line to the data. All right, well, so I'm going to graph d as a function of t squared. Well, over here I have t, so I need to establish t squared, which will be in second squared. So what I need to know is d is a function of t squared. So at 0.5 it's 0.68. So I square that and get your calculator out and square that. When you do, you get 0.46, and then square 1.02. You're going to get 1.04, and then 1.19. You're going to get 1.4, and then square 1.38. You're going to get 1.90. And you might want to carry it out to more digits if you want to. When you graph this, it's not going to really matter that much. Okay, then you have to graph these data here on the function. So I'm going to graph d in meters as a function of time squared in second squared. Very important that you label your axes properly with the variable name and the units. Okay, well, what do we know? Well, it's okay to say, well, at time t equals 0, d hasn't changed. I mean, it hasn't fallen any distance, d. d is really delta y, isn't it? So it hasn't gone anywhere. And then when d is 0.5, t squared is at 0.46. So well, let's do this. 0.5, 1.0, 1.5, 2.0. Very convenient. And notice that, d goes, and then t is going to go from 0 to 1.9, which is almost 2. So I'm going to go 0.5, 1.0, 1.5, 2.0. So on the AP test, they're going to give you a graph like this where it's going to be very convenient. The numbers are going to be fairly convenient in graphing. So at 0.5, I think it says it was at 0.46. Should be right about there. And then when d is 1.0, t is t squared is 1.04. You know what I'm going to do? I'm going to scratch this off just to remind myself. Don't graph this time, graph time squared. So 1 is 1.04. So at 1, it's 1.04. Well, 1.1 is right here, so it's just going to be 1.04. It's just going to be right about there. And then when d is 1.5, we're going to be at 1.4. So 1.5 is 1.4. And then at 2, it's 1.9. So 2, 1.9. Okay, then it says draw the best fit line to the data. This is really not fair because, you know, I guess I'm just going to use a folded sheet of paper as a straight edge. So I forgot to have a ruler handy here. Now, notice that these don't really line up perfectly. Don't freak out, okay, because data quite often aren't perfect, and they're going to want to try to give you data that aren't quite perfect. I don't know, something like this. Actually, that's not too bad. Okay, and so I'm done with this part right here. I'm all done with it. And now it says use your graph to calculate the magnitude of the acceleration. Well, when I look back here, remember the slope is 1/2 the acceleration. Right? We said the slope is 1/2 a. So I'm going to come here and I'm going to say the slope, which is equal to delta d over delta t squared. Okay? That's going to be equal. Now, here's one thing. Don't use data points to try to figure out the slope of the line. So I'm going to try to find two places where it really goes right through it. And just to make sure that the graders know, I'm not using data points. I'm using the line itself to figure out the slope. I'm going to use 0.5 and 1.5 as my points. So for my delta t squared. So t squared final, I'm going to make 1.5. And then this is going to be 0.5. That'll make my division easier. And remember, this is in seconds squared, isn't it? And then over here, I'm going to read it off the graph. So my final d is going to be almost 1.6. I would say that's like 1.58. How about 1.58 minus, and then over here at 0.5, that looks like about 0.52. I don't know, maybe 2/10 of the way up. Don't worry. I mean, I'm doing this, and I'm not looking at the solution manual, but mine are going to be a little different. Everybody's going to be a little different. As long as you're using the right process and you're really, really close, you're going to be fine. So now I'm going to get my calculator out, and I'm going to go 1.58 minus 0.52 equals 1.06 meters over 1.0 seconds squared. This is not an acceleration. It looks like it is, but remember, this is 1/2 a, so a is going to be twice this. So a is 1.06 times 2. So I got 2.12 meters per second squared. Actually, that's pretty high because I know the solution guide. Let's take a look at the solution guide. They got this. So I don't know. There's a little discrepancy there. But I'm not going to worry about it. I'm pretty confident that because I did it the right way, even if my best fit line isn't perfect, I think I'm going to be okay with that. So so I'm just going to move on. Now, it says calculate the rotational inertia of the pulley in terms of M, R, A, and fundamental constants. So here's the pulley here with the string wrapped around it, and so here's the little block M. Well, I've got a tension T. Let's talk about the tension in the rope, and then I'm going to draw the little block right here, and I've got mg right here, and I've got this tension right here. And remember, the tension in the rope, it's not mg. It's not little mg. The tension is not mg. If the tension was mg, then this little guy right here would not accelerate. It is accelerating down. So the force mg has to be greater than so ma, the acceleration of this, is going to be equal to mg minus t. Okay, so what does this let me do? Well, why did I do that? Well, it lets me solve for t. T is equal to mg minus ma. When you do the, just put, this side and this to that side, and you get this. All right, so this is my tension force. Well, it's my tension force that's causing a torque on this disc that's going to make it rotate, right? So, and we know that torque, the net torque, is equal to I alpha, I the rotational inertia, which is what I'm trying to find here, rotational inertia, and that's going to be equal to R cross F, right? Well, we don't need to worry about the cross product because everything's perpendicular and all nice and well behaved. So what do we know? We know that I is equal to R cross F over alpha. Okay, well, let's continue with this. R stays the same, but what is F? F is the tension in here, and we know what the tension is. It's mg minus ma. And what is alpha? Well, alpha is the linear speed, or linear acceleration along the outside here, divided by the radius, right? So alpha equals a over r. So I'm going to put the angular acceleration, alpha is equal to a over r, and this gives me my final answer. I is equal to reciprocate and multiply, that's going to be r squared over mg minus ma over a. Now, we know that the units for rotational inertia should be kilogram meters squared. And look what I get here. The A and the G, the units for that cancel out. So I got mg, I got m kilograms times r squared. So I have the right units. Always check the units. If the units work, you probably did it right. Or you did a lot right. Anyway, I think in the solution manual they distribute out the m. So let's go ahead and do that. So it's m r squared times g minus a over a. And oh, here's another thing. Rotational inertia, like as I was saying, is almost always some fraction of mr squared, right? Like a hoop, I mean a disc is 1/2 mr squared, right? But and you have 1/12 mr squared or 1/3 mr squared. Well, here we have this fraction right here. That's a fraction. Okay, last part, part D. It says the value of the acceleration found in this part B, along with numerical values for the given quantities and your answer to C, can be used to determine the rotational inertia of the pulley. Ooh, that would give us, like if we actually had, what they're saying is that if we had numbers for all that, like we have numbers for A, right, that 2.12, or I think the solution manual got 2.04 or whatever. But if you measure, so if you measure this, if you measured R and we know what G is, we can figure out what the rotational inertia is. So this is that I. But what we find is that when we remove, it says the pulley is removed from its support, and its rotational inertia is found to be greater than this value. So the actual, I'll put actual, the actual rotational inertia is greater than what we figured out up here. Wow. So we want an explanation for why that is. So it's actually heavier than it seemed. Now, one of the and by the way, the first time I ever took this test, I got this part wrong. Because I thought, oh, friction in the bearings, duh, friction. Friction always screws everything up, right? Not in this case. If you've got this disc and it's obviously on some kind of bearing, that it's rotating about, right? But there was friction in here in this bearing, it would make this thing seem like it's harder to move than it is, which means that the eye, the actual eye would actually be less than what we would calculate. I mean, it would seem harder to move. So friction isn't the answer. What is the answer? Look, this thing is actually harder to move than what we measured, because we measured this acceleration, which means that it seems like it has less rotational inertia, right, than it actually does. And what could cause that? Well, one of the things that could cause that, well, they said that you had a string, so here's this little mass. If the string was slipping, so slipping would cause a greater acceleration, a greater A, and thus a smaller measured I. So if the string was slipping, this thing would seem to have, based on our acceleration calculation, less rotational inertia than it actually has. So that's one explanation. Another explanation is that what if you used really thick string and you really wound a whole bunch of it on there? Well, what happens the more you wrap around? What if you wrapped a whole bunch on here? A whole bunch of string on here. Well, now your mass would be out like this, right? So now, with the same little mass here, you're going to have greater torque because the lever arm is greater. So your R is not the R of the disc, but the R extended. So this is going to have greater torque. Greater torque means greater angular acceleration, which would make it seem to have less rotational inertia than it actually has. So I don't know, you could write that out, say string wrapped around itself gives a greater R, greater torque, less rotational inertia than it actually would have. So now, if you get to this, by the way, if you get all this done, and I think all of this is very doable to part C, you get here and you get confused and you go, I don't know. Well, skip it and come back to it because it's only worth 2 points. But anyway, so I just took almost 24 minutes to explain a 15-minute problem, and which kind of seems impossible, right? Because you only get 15 minutes per problem on average. But remember, you're not trying to get 100%. So if you're cruising along here and okay, it's taken me more than 15 minutes, but I'm really making progress, I'm really scoring points, don't worry about it. But if you get to this and you don't really know, skip it and move on. Maximize your points. Okay, big ideas? Well, linearizing nonlinear data. For this part, excuse me, I'm sorry. Remember, big idea. Sometimes they give you more information than you need. If you have 3 kinematic facts, you can use the kinematic equations for constant acceleration. Linearizing nonlinear data using the linear equation, this idea here. Big idea over here, calculating slope. Big idea here, free body diagrams, equal and opposite forces, torque, net torque equals I alpha equals R cross F. Okay, so anyway, I think I'm going to stop now. So, I hope you did well on that problem. That is all.